Okay, chapter 9 is going to be covalent bonding. We'll learn about the orbitals and more specifically, this thing called we'll learn two things, hybridization and the molecular orbital model. So what we've been learning about so far are atomic orbitals. So you have an orbital in an atom and it has electrons and they're in the S, the P, the D, whatever shell, right? But if you bond two atoms together, their orbitals mingle and they actually hybridize. So we'll learn about what that means. Now, before we start, I want to talk about something very fundamental that will kind of set the table for everything else, is why do atoms bond? So let's talk about covalent because this mostly corresponds to covalent, but why do they bond in the first place? So here you see this little GIF of hydrogen. Now you have two hydrogen atoms coming together to form the covalent bond. We know that the two electrons share, yada, yada, yada. But why does that happen? If you have two hydrogen atoms that are just lone atoms, almost instantaneously, if they find each other, they will become H2. That is a much more stable molecule than hydrogen. Does anybody have any ideas of why this occurs spontaneously without any energy? And it actually releases energy. So it's kind of a hint. But so why does this happen? And this is really the reason why everything happens. Yeah, so you get it. Yeah, exactly. You're getting at it. So hydrogen likes to, I always say this word, likes to have two valence electrons. But the reason why it likes to have, or the same reason why oxygen likes to have 8, or all these atoms have these rules for how many electrons they like to have, is because originally without these electrons, they're at a higher energy state. When they come down and they bond to each other, they actually come down in energy and release energy. So when bonds are formed, energy is released. That means they're more stable. And that means that both atoms are at a lower energy state when they're closer together and when they're bound, but not when they're too close. But it's a perfect, like, happy medium. Exactly. So Isaiah, you're perfectly right. Good. So that's how we get to our bonding, because it's energetically, I've said this before many times, that it ends up in an energetically favorable state, lower energy state. Okay. So what hybridization is when you have the atoms that are ready to bond. Electrons could actually jump orbitals because this makes a better energy state for the bonding capability. So this kind of sets it up for the other atoms to bond to it and to pair up electrons with those open hybridized orbitals. So what we mean by this is, if you look at, so what we know about carbon, we can take two of our concepts that we learned. Carbon's ground state electron configuration looks like this. We can do this by hand. We know how to get this answer, right? 1s2, 2s2, 2p2. And we know to put the single arrows in each of the first two boxes. We also know about carbon that carbon likes to take 4 bonds, right? CH4, things like that. All the time 4 bonds, that's a rule. How is that happening? How's that possible? You're gonna have 4 other electrons from other atoms that are going to want to intermingle and share or be paired up with one of the electrons of carbon. That's possible here. You could just throw an electron in there. You could throw one in here, but here you can't just throw in 2 of different atoms. There's nothing to pair it with. And these other ones are filled up already. So the answer for how energetically this works is hybridization. One of the electrons from the 2s will actually jump and be excited or hybridized to the 2p. Once that happens, you have this configuration. And these 4, not this 5th one, but these 4 are going to be at the same energy level because they're kind of, the orbitals are hybridized. So hybridized just means a combination of the 2. Now, normally 2s is a little bit less energy than 2p. So if you remember that energy diagram, it's a little bit less. But once carbon is ready to take its 4 bonds, then once this electron jumps, the 2s electron jumps to the 3rd box of the 2p, then they become exactly the same energy level, and they're identical. So these identical orbitals, all these 4 that are ready to take in electrons from other bonds, are called hybridized, and we can't call them S or P, because they're not S or P. They're kind of somewhere in the middle of that energy level. So we call them sp3. So this means that you're taking 1s So not one at not this one s, just one ONE s orbital. This 2s is 1s orbital, and then p3, meaning 3p subshells, which is 3p orbitals, 1, 2, 3. So that means sp3. So you're taking an s and then 3 p's. That's this hybridization. So that's the theory of how that happens, or why that happens, because it leaves carbon in an energetically more favorable position to accept those 4 bonds. Now, in shorthand, if you have something that, and write this down, if you have something that's sp3 hybridized, that means it has 4 electron groups. That's it. That's the shorthand. Like, if you need to know on a test, quick, what is the hybridization of this carbon and methane? sp3. Why? Because it has 4 electron groups. So the term electron groups, we did talk about last class when we went over the shapes. We talked about an electron group being a valence, or a lone pair of electrons, a single bond, a double bond, or a triple bond. So those are the definitions of our electron groups. If you have 4 electron groups, it's sp3 hybridization because of this. Any questions on that? No? Good. Makes sense. All right, so we get that. So there's just a pictorial. So here's how it would happen. So you see that normally the 2s and 2p are pretty distant, and they're closer than this, but they're not the same energy level. Once the electron would jump, then they become hybridized somewhere in the middle, more closer to p. And then you have 4 sp3 hybridized orbitals that are ready to take the bonds. And this creates a tetrahedral arrangement. So another thing that you can write is, all the time, every single time, sp3 hybridized means tetrahedral for electron geometry, not molecular. So, and this kind of makes sense because what did we just learn? sp3 means that you have 4 electron groups. We learned last class, 4 electron groups. Anytime you have 4 electron groups, it's a tetrahedral electron geometry. So everything kind of comes together here. Okay, I'll give you a second for that to sink in. Any questions? No? All right, cool. All right, so describe the bonding in ammonia molecule using the localized electron model. Now, we've only learned sp3, so you can imagine it's going to be sp3, but here's the reason why. So ammonia, we know is NH3. Now, if we were to write the Lewis structure, we've seen this one before. And you have like that. So now the electron groups are a little bit different than methane, but you still have 4. You have 1, you have 2, you have 3, you have 4. Therefore, the nitrogen is sp3 hybridized. The electron geometry, Eg, is tetrahedral. Let's put tetrahedral. Okay, cool. So common questions you'll see are, in the Lewis structure of whatever, what is the hybridization of one of these atoms? So you'll see that. Okay, so yeah, it's literally what I just said. So write the Lewis structure, determine the arrangement of electron pairs using the Vesper model, meaning the electron geometry, and then from that you can determine the hybridization. So Lewis structure for NH3 we know is sp3, so sp3. Okay, the next one is called sp2. So in sp2, did I have a representation? Here we go. So we'll go back, but here's sp2. So what happens is that you're going to have one of these electrons from the filled up 2s is going to come up to the remaining. One's gonna be left over. So this is, I mean, you have different elements here, but like, let's say you have like that. One of these electrons will come up to here, and then you'll have 3 sp2 hybridized orbitals. So it's the same concept, but you're leaving out one of the p orbitals. And the reason why is because this sp2 orbital is energetically set up for a lesser amount of bonds, only 3 electron groups, or a lesser amount of electron groups. Only 3 instead of 4. So the same concept, and the hybridized orbital would only have 3 positions for electron groups. So that's seen in ethylene. So anytime, and we'll get to the shorthand. So here's ethylene right here. So basically, if you have something that's sp2 hybridized, how many electron groups would that mean? So sp3 is 4. sp2 is going to be 3. Yeah, 3. So 3 electron groups. They're all the same concept with to create the bonds, to get to the lower energy level, the electron has to jump an energy level to get enough orbitals to make those bonds and to share the electrons with the other atoms. So yeah. So another way to think about it is, if this was a math equation, each letter is the number of electron groups. So what does that mean? sp2, think about it as sp squared, right? How many letters are there here? There's S, there's P, and there's P. 3 electron groups. sp3, there's S, there's P, and there's P. 4 electron groups. So that's something like this. So ethylene would have 3 electron groups for the carbon, 1, 2, and 3. So what do you think comes next? sp3, sp2, sp1, yeah, sp. That's exactly it. So sp. So for sp, you would have how many electron groups? 2 electron groups. That's exactly right. Good, Isaiah. All right, so let's go to that. So here's your sp2 orbital. So you have your unfilled p orbital here, and then you have your sp2 hybridized orbitals. Yeah, we'll get to sp orbitals in a second, but a good definition. So we're going to be talking about another thing called sigma bonds and pi bonds. And this is important when we get to molecular orbitals, but basically a sigma bond is electrons that partake in the first bond. That's usually in the model, it's located in the center of the atom. Is it really? Well, the electrons can move a lot, you know that. So most of the time it's kind of in the middle, and that's a sigma bond. The pi bond is the p orbital electrons that are taking the place of the double bond or the triple bond. So double bonds always consist of 1 sigma bond and 1 pi bond. That's an example. So if you had, let's say, C single bond C, this would be a sigma bond. If you had C double bond C, this would be 1 sigma bond, 1 pi bond. And no, it doesn't matter which one's which, because in your picture, it's not going to be perfect. Then for a triple bond, it does matter which one's which, because you clearly have one in the middle, right? So the middle one would be your sigma bond. The 2 outside ones would be your pi bonds. And they're the electrons that are parallel to the sigma bond, and their p orbitals are parallel to that sigma as well. So that's it. Yeah. So that's a different bond. So sigma and pi bond. And we're going to be referring to that when we get to molecular orbitals. So here's an example of the double bond. Well, I mean, this could also be used for, here we go. Here's the electrons. So 1 pair of electrons is in the middle. It's a sigma bond. The other pair of electrons is in the hybridized sp2 orbital. This is the sp2 orbital. This is the 2p orbital. So yeah, so there's the other electrons. They're up there. And then when you have a triple bond, you add 2 more down here. So that's that. I'm not going to go too crazy about it. Okay, and the third one, there's actually more than just 3. We'll get into, you're probably thinking maybe, oh, we're talking about S and P, what happened to D? Well, it's coming. So sp hybridization. It involves the same principle of the jumping of electrons, but you have 1 s orbital and 1 p orbital. And if you have carbon and carbon dioxide, that's a great example. So in this case, you have sp equals 2 electron groups. And quick, anybody know the electron geometry for 2 electron groups? It's one of the easy ones. Oh, we have an answer. Not planar. Planar is for trigonal planar, right? That's when you have 3. Good, Harrison. Linear. So it's linear. Right? Because it's like for CO2, this would be linear. Yeah, because they're just the opposite directions. Okay. So that's SP. Let's see some pictures of SP. So yeah, it gives a linear arrangement. There we go. So there we go. There's carbon's sp orbitals that are hybridized for partaking in 2 electron groups. So one's going to be, and so another thing is, when you have different atoms bonding to each other, all of them are hybridized in a certain way. So in CO2's case, let's go back to this rough Lewis structure. In CO2's case, the hybridization for oxygen is going to be sp2, because you have 3 electron groups. You have 1, you have 2, you have 3. So it's going to be sp2. Meanwhile, the carbon is just going to be sp. So what we would expect from you is to have a Lewis structure and be able to determine the hybridization of each of the elements in there. And that's based on how many electron groups they have. So we already got the first 3. We got 2 electron groups is sp, 3 electron groups is sp2, 4 electron groups is sp3. Okay. All right. So nitrogen, 1s, 2s, 2p, and nitrogen looks like this. Okay. So when it's hybridized, what's going to happen is, as we know, one of these electrons will go up here. Then these 2 orbitals, since this 2p orbital will have 1 electron that is in the energy level of the 2s, it will come down in energy level, and it will create this hybrid orbital called the the sp. So sp, and it's going to have boom, boom. One of them is going to have 1. One of them is going to have 2. Then you're going to have your 2 regular 2p's, right, 2p's, and they're going to have 1 each. Okay. So this is for 1 nitrogen before the nitrogen bonds. So here's what we're going to do. Wipe that out. Look at the similarities between this nitrogen. We'll change color, or I'll just highlight this nitrogen and this hybridized orbital. You have 1 pair of electrons, 1 pair of electrons, 1 pair of electrons, and the rest are unpaired, looking for a partner. Nitrogen number 2 comes along. Same thing, because you have 2 unpaired, or 2 paired, or 1 pair, and then the rest of them looking for electrons. This is why they bond. Now, how do we distinguish between which one's which? We have, so okay, does that make sense first? Yes. Yes. It has 5 valence electrons, so that makes perfect sense, right? 5. So it needs 3. Well, it needs 3 because it needs 3 to get to 8. Yeah. But yeah, same. Yeah. Okay. Okay. So now, why do we care about this? Why is why is the hybrid orbital here and the other 2 are up here? Why are they different? And we touched on that already, because these bonds are different. This bond, the electron that bonds here from the other nitrogen, is a sigma bond. It has a lower energy level and it's a single bond. The other ones are the pi bonds, because in a triple bond, there's 2 pi bonds. Does that make sense? Because they need to make a triple bond. That's the only way they can bond together. Exactly. So we learned that the sigma bond is just the single bond. The pi bond is anything additional to the sigma bond. So in this case, there has to be 2, because there is two p orbitals left over that need a bonded electron in it. Okay, does that make sense? Everybody online? What do you guys think? Should we do another example? Okay, let's do another example. Let me think of one. Let's do O2. Okay, so O2. So O2 with the Lewis structure looks like that. A little bit different, but we'll see what happens. Okay, so we have oxygen number 1. Oh, Isaiah has a question. So just to be clear, sigma bonds are any bond past the single. No, the pi bonds are any bond past the sigma, single. So for a triple bond, it would have 1 sigma and 2 pi's. A double bond will have 1 of each. A single bond will just have 1 sigma. Sigma, single. Right? We have 4, 6. Yep, that's 6 valence. Okay. All right, this makes sense now. So I knew I had something wrong. 2s, whatever. So wait, get rid of this. Okay, so we have same thing happens. We have our 2s jumps up here. Okay, so now we have, it doesn't matter which one it goes to, we have 2 of our 2p orbitals have open spots, right? Before anything happens. In order for the oxygen to accept the correct number of bonds, one of these 2s electrons jumps up. That, whichever one it jumps up to, now becomes a hybrid along with itself, just like it always has been. So we have one of those and one like that. And then you also have this. These are now 2p's. 2p's. Like that. Yep. Okay, cool. So now what do we have? In each oxygen, we have this. So each oxygen, if we take away double bond, that makes sense, right? This oxygen has 2 lone pairs. Oh, look, oxygen has 2 lone pairs. That's 1, that's 2. What can it accept? It could accept 2 electrons. So 1 electron would be here, 1 electron would be here. And look, it needs 2 electrons, right? It's oxygen. It has 6, it needs 2 more. This other oxygen comes along, needs the same thing. So when these interact with each other, the first one, this electron that adds here, this would be the sigma bond. The other one would be the only pi bond that's left over. So you'd have, the product would be 1 sigma and 1 pi. So the next one is DSP3. So now it even gets more complicated, but we're not going to go crazy about it. Now, basically what happens here is that electrons will jump not only from S to P, but from S to D. Because in order to have enough open orbitals for more bonding to occur, so such as SF5, or no, sorry, PCl5 is a good example. And in this case, DSP3, this means you're going to have, how many letters do we have? D, which is 1, S, which is 2, P1, P2, P3, a total of 5 letters. That means you're going to have 5 bonds, which means your electron geometry, we'll write 5 electron groups. No, 5, because sp3 is 4. DSP3 is now 5. Yeah. So you're going to have 5 electron groups. That means you're going to be trigonal bipyramidal. I can spell bipyramidal like that. Boom. Okay. Any questions on that one? No? Okay. Okay, so yeah, PCl5 is a great example of that. And then the last one is D2sp3. So you can imagine what comes after 5. You have 6, which is your octahedral. So D2sp3 is going to be 1D, 2D, S, 3 Ps. That means a total of 6 letters, which means 6 electron groups. And that means you are an octahedral electron geometry. And SF6 is a good example of that. So yeah. Okay, so let's do an example. XeF4. So how is the xenon hybridized? So we'll do the Lewis structure for this. So Xe, we know it has 8 valence electrons. And we are going to break the rules. We have our fluorines, and remember, we always want to make our fluorines happy. So we are going to make a bond with each of the electrons in xenon, like that. And then our fluorines are also going to have hybridization because they made one bond as well. But they still have electrons. Okay, so who can answer what is the hybridization for xenon? How many electron groups does it have? Good, 6. So which one's that? Good. So D2sp3, right? So we have 1, 2, 3, 4, 5, 6. So 6 electron groups. Okay, any questions on that? It could ask for, okay, so good question. So on a test, what would it ask for? It could ask for this. It could ask for what is the hybridization of xenon. It could ask for what is the hybridization of fluorine. It could ask for what is the molecular or electron geometry of this molecule. That's about it. Or it could ask like how many lone pairs of electrons, things like that. Things that you would need to know the Lewis structure to figure out. Mm-hmm. Correct. Good. So yeah. Yep. Okay. So for fluorine, the hybridization would be sp3 because you have 1 electron group, 2, 3, 4. That's going to be sp3. And then Isaiah, to your question, the d orbital can extend to 5, right? Yes. You mean 5 subshells? Yeah. 2 electrons each, make total 10. Yeah. But also 5 electron groups. Yes. Yeah. Well, no. Oh, no. Well, D5sp3. Good question. I don't know. I never heard of that one. I guess technically it could. No, it would, no, wait. Yeah, I think it could. Yeah, good. That's a good point. Yeah, I think it could. Never seen it before, but I think it could. And maybe, I'm not sure if that's energetically stable or not. It might not be, because I don't think there's any atom in nature that can have that many bonds or that many electron groups. And if it did, its formal charge would be really high and it wouldn't be stable. So that's a good concept. I mean, in concept, yeah, that makes sense. Okay, so we get that. We know it's D2sp3. So, yeah, basically for solving these kind of problems, I mean, just draw the Lewis structure. We know how to do that. Then determine the arrangement, Vesper, and then whatever hybridization it is. So here's just a little chart. If you have electron pairs, you have, or electron groups, you have 2. You have a linear arrangement, and it's always sp. If you have 3, it's going to be a trigonal planar electron geometry. I'll put EG here for electron geometry. And then you'll have sp2. For 4 electron groups, you're going to have tetrahedral, and then it'll be sp3. So we kind of went over that's just, and then continuing for 5 electron groups, this is going to be our EG, trigonal bipyramidal. DsP3. 6 electron groups, octahedral, D2sp3. So those are our main 5. Okay, any questions before we continue? I know the concept stuff is kind of difficult. And it's really tough to explain. So I feel bad. What I want to do is, it's cool. So I want you guys to know it. Well, the videos help, but I want to make a video later. I want to make an explanation video of it later. I'll do that. That'll be my homework. Because I want to make it like really concise and make sense. Okay, but that's an aside. All right. For these, let's do some hybridization practice. I'll give you 5 minutes or so to not listen to me talk and figure out the hybridization of each atom and describe the molecular structure, meaning give me both. And Logan, yeah, I'll make a crash chem on that actually. Yeah. But that's too, it's actually too long. It would be too long, but I'll make a video on it. And also, guys, another thing, if you've been following the YouTube channel, my YouTube channel, I put on 4 videos on really good homework problems that were from chapter 4, 5, and 6 that are kind of really comprehensive on everything, on like the stoichiometry, on like the gas law, stuff like that. So it kind of incorporates everything. So definitely look at those. And they're not on Canvas. So subscribe. Let's get famous with 50 subscribers. I think I have 49, so I'm close. Yeah, for this molecular structure, do the molecular geometry and electron geometry, just for practice. I'll give you 5 minutes. Carbon monoxide, we're going to have C triple bond O, and then you're going to have 2 electrons over there on each side. And in this case, you're going to have formal charges. So that's why carbon monoxide likes to stick to a lot of things. Carbon monoxide actually binds to, the reason why it's all a little aside, you know why carbon monoxide is deadly is because it bonds to your hemoglobin better than oxygen does. And the reason why is because it has formal charges and it's smaller than O2, or it has a different arrangement than O2. It's the hybridization, and it actually has to do with hybridization. So the hybridization of carbon here gives it, and with these lone pairs, actually gives it a formal charge, and then the oxygen has a formal charge also, making it very reactive, and it binds in the same pocket on hemoglobin, on the hemoglobin protein that our oxygen does. So it blocks your oxygen from being transported to your tissues because carbon monoxide is actually more potent to your hemoglobin. So that's pretty interesting. But anyway, hybridization. What is the hybridization of carbon and oxygen? They're the same here. Are there? Well, there's 3 total, yeah, but on carbon, how many? Or oxygen? Each. Yeah. They share 1 in common. The triple bond. Yeah, so each one will be sp. Good. And then the arrangement, what would the, I mean, I guess there's only 2 atoms, so you can't really think of a shape, but if you were to have a shape, what would it be? Linear, yeah. Okay, so next, BF4 minus. So we have boron in the middle. Again, we're going to force these fluorines together. And we're going to have 1 extra electron that's going to be on the boron. So boron normally has 3 valence. Now we're going to give it a 4th valence. And they're all going to bond to the fluorines like that. Three A. Yeah, that's right. Yeah, so good. So boron, I think Angela said, is going to be sp3 hybridized, right? Because it has 4 electron groups. And the fluorines, what about them? And yes, tetrahedral. What about the fluorines? Are they, what hybridized are they? Good. sp3 also. Good. And it's because, and well, I mean, so Isaiah, it's a good point. I mean, you really can't say a shape for one of the peripheral atoms. It's only for central atoms we say shapes, but its electron geometry would actually be tetrahedral. We really can't say a molecular shape around fluorine because the whole molecule has its own shape. That's another key difference between those things, that electron geometry we can say for any atom almost, but except for hydrogen, because it just has one group and it's just, I guess it's linear, but you really can't say. But for other atoms like fluorine, even though it has one bond, we could say it has 4 electron groups, and those electron groups are arranged in tetrahedral arrangement around the atom. But we can't say a molecular shape except for the entire thing, which is tetrahedral. Okay, next one is XeF2. So again, we have to force it. So 1, 2, 3, 4, 5, 6, 7, 8. Fluorine. Like that. And then we have another fluorine over here. That. So how many? So what is the hybridization of the xenon? sp3. What did you? This is 1 group, 2 groups, 3 groups, 4, 5. Good, dsp3. Nice. So that means 5. So it's the number of letters. Yeah, and like the superscripts are like cubed, for example. So D, S, and then 3 P's. That's 5 things, 5 electron groups. And then the fluorine will be 4. All right. So we talked about that already. Talked about that. Oh, whoops. Okay. Okay. Which of the following? We'll do more practice. Which of the following contains a nitrogen that is sp2 hybridized? So NH3, we kind of talked about that one already. What's the hybridization of nitrogen in NH3? Good, sp3. It's got 1, 2, 3, 4. So it's not sp2. NO3 minus. So NO3 minus, you have nitrogen in the middle. You're gonna have another, you have 2 of these double bond oxygens, 1 single bond oxygen to have this negative charge on the oxygen. It'll have a formal charge of -1. And then what is the hybridization here for nitrogen? Good, sp2. You have 3 groups, 1, 2, 3, sp2. So that's our answer. Good. And we talked about N2 being just sp, and then this nitrogen is also sp. Okay, good. I think we're getting the hang of it a little bit. One more. All right, what's the hybridization of chlorine in ClF3? So again, this is one of the ones we have the 4 single bonds with fluorine. And then chlorine has, so we'll start over. Chlorine has 7. So 1, 2, 3, 4, 5, 6, 7. You have 1 bond, 2 bond. Oh, my pen. It ran out of virtual ink. There you go. 3 bond. Okay. So now we have what is the hybridization here for the chlorine? Yes, dsp3, because we have 1 electron group. I'll highlight them. 1 electron group, 2 electron group, 3 electron group, 4, 5, dsp3. Okay, cool. I think we're getting the hang of it. Yeah, it's 0. We know that. So that question is kind of stupid, but like sp3 hybridized, atoms that obey the octet rule that are sp3 hybridized, such as like methane, right? You'd have no pi bonds, you have no double bonds. Okay, so here's just a summary on hybridization. You see all of the different hybridized orbitals in play. So like it's something like a methane where carbon's bound to 4 different things, sp3. Carbon's bound to only 2 things, sp2, or if anything's bound to 2 things, or has 2 electron groups, you have sp. sp2 is when you have 3 electron groups. This nitrogen would also be sp3. That's not a good arrow. Whatever, you get the point. And then this oxygen will be sp2. Okay. Cool. All right, so it's got limitations. Yeah, because it's tough as hell to understand. But anyway, so what we can do is we can talk about the molecular orbital model, which is pretty neat. It kind of tells us, it can tell us the multiple things. It can tell us the magnetism of a bond, whether it's paramagnetic or diamagnetic. So just to remind you guys, so paramagnetic, and they will ask things about these on the test. So paramagnetic means it has one or more unpaired electron. And then diamagnetic is all electrons paired. Okay. So we can figure out this. We can also figure out if a bond will actually occur in real life based on the bond order. So we'll learn about that too. So let's get into the nomenclature, or not the nomenclature, the way it's written, or the model itself. Okay, so this is what they look like. What's going on here? So on the left, we have an increase in energy. So we have our lowest energy here, which makes sense. We call that the bonding molecular orbital, because we know when atoms like to bond to each other, they have a lower energy state because the bond is favorable. So the electrons that partake in that bond are decreasing their energy level, which makes sense. Then you have the electrons that are in element A and then element B, or in that orbital of element A and element B, or atom A and atom B, whatever. And then you have your thing called an anti-bonding molecular orbital. These mean that they're electrons that are not partaking in the bond per se. They're kind of the lone pairs. They're called anti-bonding. And they're going to be at a higher energy level because they're not bonding. The bonding is favorable. But yeah, that's all. That's it. You can get more complicated, but no point. Okay, so the way we're going to do this, for hydrogen is the easiest one to look at. And I'll blow this up for those of you who are looking online. So hydrogen has one electron in the 1s orbital, right? So you draw your 1s. It's got one arrow, 1s, it's got one arrow. Then you draw your, what we call these is your sigma 1s, because it's only going to be a sigma for hydrogen, because this is 1s. There's only a sigma for 1s. There's no multiple bonds, double bonds or anything. And then we call this one, the anti-bonding, we call it sigma star. That, and we actually call it that, it's a nomenclature. So star means anti-bonding. So the sigma star and sigma 1s star and sigma 1s are the molecular orbitals in the H2 molecule. So in every place you have a bonding orbital, you need to have an anti-bonding orbital. And the reason why H2 is favorable, because all of the electrons end up in the lower energy level. So look where they end up. So basically the way you do this is like kind of like a chart. You take the electrons and you put them in the lowest energy level first, and then you put them in going upward. That's basically how it works. So if I were to give you this as an example, you would do this. And this is a really crappy draw. Oh no, what did I do? Yeah, so you do this. And this would be sigma 1s star. This would be, or you could even just write sigma and then sigma star. And then this would be one electron here. We know that because they're hydrogen. And then you would literally just do this. They would go in the lowest first. If there was more electrons, you would fill up the top. And there's more, when we get to pi orbitals, there would be more to fill in. So we'll get there when we get there. Okay, so does that make sense? Basically, you just fill in the arrows. And the reason why we're filling in the arrows is we can tell if a bond will actually occur. In this case, hydrogen to H2 is very stable because all the electrons end up in a lower energy level. And we can calculate something to figure this out quantitatively called the bond order. So the bond order is used to indicate bond strength. And the way you figure it out is the number of bonding electrons, so the number in the lower tiers minus the ones in the upper tiers divided by 2. So for that hydrogen example, you had 2 in the lower tier minus none in the upper tier divided by 2, which equals 1. So a bond order of 1 means it partakes in 1 bond, and that bond is favorable. Really, the only thing that's not favorable is if you have a bond order of 0. So a bond order of 0 means there's no change of state in energy, or there's no change of energy state going from the reactants to the products in the bond. Therefore, why the hell would the bond occur in the first place? There's no reason. So, or if in some cases, well, there's no cases where anti-bonding could be more than bonding, but they could be equal. That's not favorable. So does that make sense? Kind of. Okay, moving on. All right, so there's another one. So we can have a thing called H2 minus. It's less favorable than H2, but here's why. One of those hydrogens now has a second electron. So you'd fill up your bonding orbital. That extra electron would have to go in your anti-bonding orbital. Therefore, your new bond order is going to be 2 minus 1 over 2, which is 1/2. The bond order could be 1/2, it could be 2/5, it could be fractions. As long as it's not 0, then it is possible to happen in nature. The smaller it is, the less likely it is to happen. But if you're at usually whole numbers 1, 2, 3, 4, then it's pretty stable. So here is, yeah, so tell me about this one. So let's figure out the bond order. This is the helium-2 atom or molecule. And have you guys ever heard of helium-2? Be honest, have you heard of helium-2? Have you heard of it? No, you haven't, right? No one's heard of helium-2, right? Yeah, that's because it doesn't exist. Here's why. Here's how we know it doesn't exist. We can tell from this, if we get good at this, if any molecule exists or has a likelihood to exist. And the reason why is because helium has both of the electrons in 1s, 1s2, right? Put them in this molecular orbitals, you have 2 electrons in the bottom, 2 electrons in the antibonding, the bonding and the antibonding. So then the bonding electrons is 2, antibonding is 2, divided by 2 is 0. If your bond order is 0, it can't happen. So it's not stable, can't happen, because there's no benefit of it happening. So every bond that forms has to release energy in order for it to be stable. I mean, technically, you can force helium-2 to become a thing. I'm sure they've done it, but it won't stay like that. It'll be instantaneous, and then if you get rid of the energy, that's holding it together, then it'll go away. So good. All right, next one we could do more. So for something like B2 is pretty stable. But here's what happens now that we make it more complex. So when we introduce more orbital or more subshells, you have to add more of these. So, okay, disclaimer, you're not going to have to draw these. You might have a picture of them on an exam, I imagine, if the picture loads, because Canvas sucks at loading pictures. But if the picture's there, you'll have to interpret it. Maybe calculate the bond order, or calculate if it's, or tell them if it's paramagnetic or diamagnetic, things like that. You're not gonna have to draw these on your own. If we were on paper in a normal class, maybe you'd have to. But even with work, I can't imagine you're not gonna have to do that. Okay, so in boron, let's draw the electron configuration for boron real quick. So boron, you have 1s2, 2s2, then it's 2p1. So we have to do that just for the valence electrons. We ignore the 1s, just the valence electrons. The 2s2 would be here. You'd have each one of the bonding borons would be 2s2. It would have 2 electrons filling up the bonding and the anti-bonding. That we just went over, that's not favorable, but that's not the only thing that happens. We have more things, right? We have 2p1. So we have a 2p1 electron here and also here for each boron. Now, the way they draw this is in terms of energy increase, right? That's on the y-axis. So you have to draw your, I'll just tell you why, but okay, this is why you won't have to draw it in person or on a paper, because it's weird. For boron and carbon, boron, carbon, nitrogen, it looks like this. For oxygen and fluorine, the sigmas here are flipped with the pi's. And that's because that once you get to oxygen, you're now filling, so like this is where you are at nitrogen. Once you get to oxygen, you're filling this. So then putting electrons in the pi orbital, the remaining two pi bonds are more favorable. So it's lower energy to put them in those bonds. But again, that's a little bit beyond the scope here. But let's go back to this. So you have this 2p1 electron, and it would just go in the sigma, the bonding sigma 2p orbital. So here's your p orbitals, right? So here's the way we can think about them. You know, there's three slots for p orbitals, right? One of those slots is a sigma bond. The other two are pi bonds. Easy way to think about it. That's exactly what this molecular orbital diagram shows, is that the bottom one, the lowest energy one, is your sigma bond, because that happens first. Any additional bond would be your pi bond number 1 on the top and pi bond on the bottom 2 to make your triple bond if it does occur. So in this case, you don't have a triple bond between boron and boron. It's only going to be, in this case, a double bond, because you're going to have here and here. You have two paired bonding electrons. So it would be a double bond. And what we can figure out is the bond order. So the bond order of this would be the sum of all the bonding, which there's 2 bonding here and 2 bonding here. So that's going to be 4, minus the anti-bonding, which is 2. There's no anti-bonding over here. Over 2, which is 1. So the bond order is 1. Okay, does that make sense? Okay. All right, so another question would be, is this paramagnetic or diamagnetic? So paramagnetic means you have unpaired electrons. So is this paramagnetic? And keep in mind, where you're looking for the electrons is here. We're not looking at where they started out. We're looking at where they're bonding. So anything unpaired in the middle? Yeah, exactly. Yeah, everything's paired. Good. Good job, Isaiah. Yeah, so everything's paired. Exactly. So that gets us into a definition. So paramagnetic, unpaired. Diamagnetic, all paired. So just know that. Okay, so here's examples of, here's what I was getting at before with so here's the diatomics. So here's the top row of diatomic molecules where you have boron, we went over, where it has, wait, what did they do? Did they draw it wrong? B2. They drew it wrong. Wait, which one's right? Holy crap. They actually, something's wrong here. Because look, so B2, is it, hold on. I need to double check. B2, molecular orbitals. Oh yeah, wow. Okay. This is wrong. Weird. That's the textbook for you. So it's actually the opposite, where not everything's the opposite, but the pi's are where the sigmas are supposed to be. Not a big opposite. Remember I said that when you get to oxygen or fluorine, it switches? That's still true, but it switches the other way. This is the one, they put the wrong thing in here. This is the molecular orbital diagram for, in terms of the energy. This is the one for oxygen and fluorine. They use it for boron. They shouldn't have done that. So this is correct. So I'll walk you through it. For boron, carbon, and nitrogen, not oxygen and fluorine, it goes in the level of, I'll draw them out on the side. So you have, every case you have your s electrons, which are sigma and sigma star. And you're always going to have these filled up. You have 2 there, 2 anti-bonding. Then you get to your pi orbitals, or your p orbitals, which in boron, carbon, nitrogen's case, your pi bonds are actually lower energy than your sigma bonds. Then your sigma bond is a little bit higher energy than your pi bond. So then your sigma bond is going to be there. Your sigma, this is going to be your pi. This is going to be sigma. This is going to be sigma star. And this is going to be pi. Oh, flip those. So it's going to be pi star, sigma star. Kind of like it's drawn here, over here. Okay, so if you were to do boron the correct way, you would have your bonding orbitals for sigma and sigma star filled up for the 2s. When you get to p, you're going to have to fill 2 electrons, because remember boron is 2p1. So you're going to have 1 of the electrons from each boron go into these pi orbitals. These are these pi bonds, which would be 1 here and then 1 here. And that would be in 2 of the boxes, like out of the 3 boxes. Does that make sense? I know it's kind of a flip-flop because the book got it wrong there. And then that's the case for carbon also. So carbon, you're adding another electron. So you're adding that second electron from each of the carbons goes to the open slot. So one would be here and one would be here if you had carbon in C2. If you had nitrogen, you're going to add another one, and then you'd have 1 from the first nitrogen, 1 from the second nitrogen. So should we do an example? Yeah, okay. So I think we have those. There we go. Let's do phosphorus. Let's do P2. So phosphorus is underneath nitrogen. The nitrogen is this arrangement. So we have the traditional arrangement, not the oxygen fluorine arrangement. So we'll do Ne2 also, but when it's a little bit easier. But let's do phosphorus first. So P2. We're gonna have, let's draw a configuration first. We have 1s2, 2s2. All right, we're gonna be 3s. So 3s2, 3s2, 3p3. Because underneath nitrogen, right? So we're gonna do this. So it would be our 3s2, and then we have 3s2. We have our sigma, and then we have our sigma star, like that. And then our 3s2 is filled up in both cases for both phosphoruses. And then we have our p orbital, right? So our p orbital is going to have 1, 2, 3, 1, 2, 3, and electrons it will have 3. So it'll be 1 in each of them, like this. Does that make sense? Okay. So now in terms of which molecular orbitals are we filling up first, this is where the discrepancy came into play. So we're going to have 2. These are going to be pi orbitals. So you have pi, let's call them pi's. Then you're going to have your sigma, which is a little bit higher energy. Sigma. Then you're going to have, your pi stars. So pi star, and then sigma star, which is antibonding. Okay, so that's what it would look like traditionally. All right, so let's draw electrons. So all we do after we figure this out, everything is easy. You take these 4 electrons here, 1, 2, 3, 4, done. There's 6 electrons here, 1, 2, 3, 4, 5, 6. Done. So what do we know? We know that there's going to be, is this paramagnetic or diamagnetic? Good, diamagnetic because they're all paired. Bond order. So bond order is the bonding minus anti-bonding divided by 2. So bonding is going to be how many bonding? There's 6 here, and then how many total? These ones count too. Not 10. 10's total. 8. Good, because you have the bonding electrons. I'll highlight them. 2, 4, 6. Yes, these were anti-bonding, right? So you're going to have 8. So 8 minus these 2, which is 4, divided by 2, which is 2. So this, is it favorable or not? No, 0 is unfavorable. So, okay, so you're confusing the formal charge. Yeah. So this class is very confusing. I understand that this particular chapter is very confusing. So formal charges, we want to minimize them. Bond order, it needs to be big. Bond order is good. Bigger bond order, more stable. Bond order of 0, that means there's no, think of it, there's 0 order to the bond. Can't exist. Okay, that makes sense, guys, online? Okay, hopefully it does. All right, so for neon 2, so Ne2, we'll do that one now. So neon is just going to be, well, neon, we can just modify this one, actually. So neon will have everything filled up because it's noble gas. So it'll have your 3p will be filled up. Well, even though neon's, I get it, neon's 2p, I get it, but let's just say this is now 2s, and this one is 2p. Let's just say, just to save time. Okay, so now we're going to fill in. We have 12 electrons, and we're going to fill everything up. So we have 6 so far, 7, 8, 9, 10, 11, 12. All right, so where you have everything filled up, the bond order is 0. And you can calculate that. You have the same number of anti-bonding, then you do bonding. And if its bond order is 0, that means this can't be. So neon 2, any noble gas as a diatomic molecule, that's not a thing. So if ever you see that on an exam, you know that that's not a thing. Okay. Any questions on that? No? All right, almost done. So which of the following is paramagnetic? So let's just save time. Actually, means, well, let's do them. Let's do them. I'm being lazy. Okay, so let's just draw, since they're all on the same level, we can just draw the same kind of thing for all of them. So hydrogen first, and we'll fill it up as we go. So we have 2, well, let's just say S. Let's not specify 1s or 2s because hydrogen's in 1s, and the other ones are in 2p. So we'll just say S. We have our sigma, and we have our sigma star. And then for these, we have our pi bonds, which is going to be pi. Then we have sigma, and then we have pi star, and then up here we have sigma star. And this is our p orbital, so we have 3 open slots for electrons. Okay, now hydrogen first. Hydrogen we know as 1 here, 1 here, or 1 up here. So then our 2 electrons would go there in our bonding orbital. And is this paramagnetic? Are they unpaired? Yes, question. What do you mean on these ones? So these are from the atom. And we're writing down the ones that are in the atoms, and then we're putting them into their orbitals. Yeah. Yes, good, because they're all paired. So that's not the correct answer. All right, next one is boron. That comes next. So boron this is filled up with boron. So then we have, this would also be filled up, and then we're up to here. So this is going to be our p orbital. You'll have one in each p orbital. Then we put those in there, you'll have like this. Or, well, they're both facing off. Pretend they're both, doesn't really matter. They're both there. So is this paramagnetic or dimagnetic? Good, because we kind of went over this example already, but they're unpaired. So this is going to be your answer. Now going forward, nitrogen. So nitrogen is going to be, or no, carbon's next. So carbon will be here. 4 valence electrons. You have 1, 2, 2 down here, and then 3, 4. So we're going to fill in these. You add another electron to these. The way you would do it based on off-bound principle is you would do that and then do that. And this would make it diamagnetic again. That's why carbon's not the answer. Then nitrogen, adding another one. Then you have add 2 more. Then those 2 added electrons will now go to the next highest energy level, or next lowest, which is the sigma bonding, like that. Still making it diamagnetic. Yeah, kind of. Okay, all right, cool. All right, so here's just more examples. Here's carbon, we saw that already. Here's hydrogen, we saw that already. Okay. Statements is false. Yeah, so atoms or molecules with an even number of electrons are diamagnetic. I don't know about that. I don't know. What do you guys think? Think about that. Too tired to think about that. With an even number of electrons. So what about, so diamagnetic means they're all paired, right? What about carbon? 4. 4A, yeah, it's cool. So it has 4 valence electrons, and the first 2 are paired, right? Then the next 2 are in the p orbital, and look at that, unpaired. So that's not true. Yeah. Then conversely, atoms with an odd number of electrons are paramagnetic. That's always true, because there's no way to have an odd number and have everything in 2s, right? So that's true. Paramagnetism cannot be deduced solely from the Lewis structure of a molecule. I mean, that's true. Until we got our molecular orbitals, we didn't know how to figure it out, really. For a molecule, for an atom, we did, but for a molecule, that's where we learned this from. So that's one of the key skills we learned today. Now, out of all this convolution, you learned something at least. So paramagnetic molecules are attracted towards a magnetic field. Yeah, that's just the definition of them. Yeah, because they're unpaired, so that they have a pole. Okay, cool. Okay, so there's a little twist on it. Heteronuclear. So we've been talking about homonuclear molecules so far, meaning the same atoms in diatomics. You could also do the molecular orbitals for heteronuclear. And this is where it actually gets really confusing, because if you're thinking about it, he's like, professor said that in oxygen and fluorine, there's different rules for which one comes first. And then for boron and carbon and nitrogen, it's the opposite. What if you have 1 carbon and 1 oxygen? What happens? Well, it gets weird. Basically, I think it picks the oxygen one. But so here's what they would. So for simple molecules like HF, it's not too bad, because you're just going to have 1 bond, and those bonding electrons are going to be, one of them's going to be in the 2p, the other one's going to be in the 1s, and we know this, and it just kind of creates we can't have them equal in the same energy level, because one's a p, one's an s. But and also it's just kind of just like mixed. It's the same thing, just mixed. Think about it that way. We know that it's stable, and we can tell it's still the same things. We can tell paramagnetism, stability based on bond order. So really the same things. And then we know about where the electrons are. So this can tell us where the electrons like to be more. So for fluorine is down here. And there's a reason why the fluorine 2p orbital is at a lower energy in this bonding case for bonding orbitals than hydrogen's 1s. And that's because of electronegativity. Because fluorine needs only one more electron really badly. So it's very attracted to electrons. So that's why when you have bound fluorine, the energy level of the fluorine is going to be very close to the bond, or the bonded electrons, meaning your electron cloud will be very close to fluorine in comparison to hydrogen, making your dipole. Oh, look, polarity comes back into this. So